How is the recursion theorem used to define addition? Okay. Let's do that then. Switch to the So how is the recursion theorem used to define addition? Okay, so the recursion theorem is stated in a particular way. So let's review that. So let A be any set, and when we're defining arithmetic, A will be omega. So when we define arithmetic operations, but it doesn't have to be omega, and we pick a starting element, B in A, and a function that's going to give us always the next thing. So this is the data here. This is what we're given. And the conclusion is that there is a unique function. So there is a function and it's unique. And that is going from omega into A. And it starts out with the starting element. And at successive stages, we apply the next function, the nexting function f of h of n. And of course, n plus 1, we're going to call this, we're going to name the successor function. Successor of n is n plus 1. So the picture lined up is we have our natural numbers in the domain of h over here. We start out with b, and we look at f of b and f of b, and so on. And now at the nth stage here, we apply f, as it were, n times. So to get addition, we start with A as omega. So, I mean, are there any questions about the recursion theorem before I go on to just answer the question about addition? Then to define addition for arithmetic, we will take A to be omega, f will be the successor function itself, and our starting object will be the number that we're starting our addition from. we define for each n in omega this function an of x. So we'll take in the above, in the recursion theorem, we take a as omega, and f will be the successor function there. And the starting object will be n. So this will be my h that we're trying to define. This will be for 0, there'll be the starting object. And for s of k here, we'll actually apply f of an of k to the previous value that we know, and f itself is the successor function in this case. So again, this we're going to say is an of k plus 1. It should be our usual notation for successors. So in this case, in the successor stages, it just happened to be that the f function was itself the successor function. And of course, that's not going to be the case when we define other operations. So similarly, multiplication, we're going to we'll take again so I'm just trying to think of the right thing to say here. We just start out with, here's our starting case. We're going to call that m times 0, but this will just be 0. If I want to define mn at the successor case here, I assume I already know mn of k. Well, and now I'm going to add that to n. So the other thing I'm implicitly assuming is I know all the addition functions of this form. So I've assume I know, I've proven the properties that I need for addition, and then I can apply and define multiplication from addition, like this. And exponentiation also similar. Okay. All right. Are there any particular exercises to do with the recursion theorem or so on you'd like me to go over? Now would be a suitable point to do that. Okay, let me do something then that was similar on that homework. I think I set 212.1. I'll do 212.2. So what did 212 ask for? Prove for any n, m, and k. Well, two things. If n was less than m, then n plus k is less than m plus k. So it's proving that addition is strictly increasing in this first variable. Right? And as long as k is bigger than 0, we can do the same for multiplication. And as I always say for these kinds of inductions, do it on the last variable that you can see floating around in the statement of what you need to prove. So we've got n, n, and k here. Do this by induction on k here. So, okay, why don't I do both parts? So we do 1. And so k equals 0, usually the base case, but sometimes 1 is the base case. Well, in this case, this is now kind of trivial. Well, n plus 0, this is 0, this is n. And if you ask me why, I would appeal then to the definition of an, right? Definition of an tells me n plus 0 is 0. We're given that this is less than m by the assumption here. So, but this is also n plus 0. Right? And again, if pressed, I would say this is because of the am function. But I think for an answer, you could just say it's trivial. N plus 0 equals n is less than m equals n plus 0. Now we assume that it's proven for k, and we prove it for k plus 1. Assume it's proven for k. And we have to prove it for k plus 1. Now, when I say 1 proven for k, I mean for any n and m. So fix n less than m. Right, so just take an arbitrary n less than m, and we want this with k plus 1 in here. So by assumption then, we know this for k, n plus k is less than m plus k. But then this implies, right, if I go one more beyond here, the successor of n plus k here, this is going to be less than or equal to m plus k which is less than the successor of m plus k. Here. And this is what we're calling as m plus k plus 1. And this is what we're calling n plus k plus 1 here. And now I just use the associativity law here and here. I guess I don't really need to say this bit here. If we're assuming always that the successor function is increasing. So this will give us it for n plus 1. So that's 1. And one just does the same thing for multiplication. Right? So what have we got to do? We've got to do the same thing here for k. Sorry, for now k is bigger than 0. Right? So k equals 1 then would be the base case. Now you just say, again, it's kind of trivial. N equals n times 1. That's by the definition of multiplication here. So this is less than m, which is m times 1. So for k equals 1, we're done. So assume proven for k, and we prove it for k plus 1. So again, fix n less than m here. And we assume n is less than m. And then this implies n times k is less than m times k. So the idea is you just plug in what you want, the k plus 1, and you use the rules of arithmetic we've already proven to hopefully get the desired inequality or whatever it is you're trying to get out on the other side. So n times k plus 1, and this is n times k plus n. Now this is by the definition of mn. N times the successor of something is n times the previous thing plus n. Okay, so let's see, what should we say next? This is, as n is less than m, this is less than n times k plus m here. So if I'm doing this one the right way around, this is basically by part 1. Where we proved that addition was increasing. Let me just think for a moment. Whether I want to do that this way around. No, I think I don't want to say this bit next. I think I'll use the inductive hypothesis next here. Well, I'm using our inductive hypothesis and part one at the same time. By assumption, this is less than this here. And by part one, if I add L onto this, it's going to be less than L added onto this. Well, here I'm adding N onto this, and it's less than N onto this. So I'm using the inductive hypothesis and part one. In part one, replacing N and M by N times K and M times K. Right, to slightly over-explain this last bit here. Okay, but then because addition we've proven is increasing, this is less than this here. And this is just M times K plus 1 over here. So just a slightly trickier move just at this point. Okay. Well, let's say a bit about well orderings then, unless there's anything more about the recursion theorem. So sort of general theory of well orderings. So what are they? These are strict total orders. And any non-empty subset of the field has a least element. Non-empty subset of the field of the well order has a least element, whatever the ordering is. Okay, so our canonical example of this is the natural numbers. So note what this implies. So look at exercise 3.2 says if you're given a well order, then there's no descending sequence through the ordinal. So there is no set of objects xn with, for all n, xn is in A, and for all n, xn plus 1 comes below xn. Okay, so this is just, I mean, if I now take the set X, to be the collection of the little x's, so if this satisfied 1 and 2, then clearly X has no less than least element, because given any one, there's a smaller one. X would have no least element. Thus, this thing here would be not a well order. All right, so that will be a contradiction. I mean, there's a little point to the, there is a little point to the exercise, which is, you might say, well, why didn't he define well orders like this? Why didn't he say a well order is a strict total order? Well, there's no infinite descending chain like this. Well, you could, right? But you need a certain, little bit more set theory to define it like that. Because I would have to, if I wanted to show that this definition, sorry, if I wanted to show that the ordinary definition of well order implies this, if I wanted to show they were equivalent, right, I would have to have a way of going from the general definition to picking out a sequence like this. And that picking out involves an infinite amount of choosing. So again, that's what set theorists say. We're using the axiom of choice to do that. So we could perhaps have used 1 and 2 to define when a strict total order was a well order. But to do that, we would have needed some choice. But to show sorry, I'm just thinking about what I'm going to say. Yeah, to show that if this thing here was not a well order, then there actually is a sequence xn as above. This would imply we'd have to make an infinite number of choices. I mean, what would we do? We'd be saying here, if this is not a well order, okay, pick any x0. What would we do? We'd pick any, I'd be thinking of this as like a function. I'd be picking f of 0 in x. Call that x0 in a, right? Suppose if x0 is not least in a, then I'd pick something below it. I'd carry on like this. I pick fn plus 1 is xn plus 1 coming below xn. So I'd slightly jumped something here. If this is not a well order, let x be contained in A, x without any least element. X without a least element. So if our A here is not a well order, there's a non-empty subset here, which is without a less than least element. So I pick x0 in this x, but x0 is not least, so there is something below it. So I pick an x1 that's below it. x1's not least, etc., etc. So my set there of these xn's becomes a descending chain through x. So we have that the range of f is a descending chain. So this would mean that we've got a chain that satisfies this 1 and 2 up here. But I have to justify the existence of f. And you might say, why not? I mean, this looks a little bit just like a recursion, right? But in the recursion scheme, there was a definite function which told us how to pick the next thing. We were given a function that told us what the next thing was. If you think about this, there isn't a function that tells us what the next thing is. There's just this vague pick something. So there's no definite function that tells us how to go from x0 to x1. It just says pick something, and that's vague. And it turns out that vagueness is important. Right? You have to assume the axiom of choice to allow yourself to define this function here. So there's no definite way to pick xn plus 1 given xn. Right? It's vague. So we can't use the recursion theorem here. So we cannot use the recursion theorem here, which requires a given as part of its data of the function that says what the next thing is. The next function f. So here we need the axiom of choice. I won't specify that anymore at the moment. Here we should need an axiom to do this choosing for us, to justify f. Okay, so that's a little bit of an aside right here. But it shows that if you wanted to go from a definition of well order where there are no infinite dependent sequences like this and prove that this was equivalent to our definition of well order, you would need an axiom. What is the axiom of choice? I'm asked. Axiom of choice, this will come up in, I don't want to talk about it too much now because it's not lecture time. It'll come up in chapter, is it 5 or 6? Is it later on in the course? Chapter 5. We'll be covering that more thoroughly. Okay, let's look at exercise 3.5. Find an example of two totally ordered sets which are not order isomorphic, but each is order isomorphic to a subset of the other. Each is order isomorphic to a subordering of the other. So this might look a little bit peculiar at first. I've got some ordering here, A, and I've got B, and there's no bijection that preserves the order between them. Okay. But I can find order isomorphic to a subset of the other. It means that there is some one-to-one function from A into B, which is an isomorphism, and likewise there's a one-to-one function from B into A. But there are F from A into B, which is one-to-one, So then F will be an isomorphism between A and its range. And its range will be a subset of B. And similarly from G going the other way. So then we should have that A was less than. This would then be isomorphic to range of F with the ordering on the B side. And likewise the other way around. Range of G on the A side. So A and B is isomorphic to a subset of B, and B is isomorphic to a subset of A. So it perhaps only looks peculiar at the beginning because there are, well, you know, there are many examples like this. So the one I've suggested in this answer sheet here is I take, for A, I will take the rationals in 0, 1, and it'll be the usual ordering. And for B, I'll just take the rationals in the so this is the open interval. 0 is excluded and 1 is included. Here it's the other way around. 0 is included, 1 is excluded. Again, the usual ordering. Now, x1 with less than is not isomorphic to x2 less than. And you might say, oh, how do I show that? Or what do I say? Well, to show that two things are not isomorphic, you need some feature, which means you can't map one onto the other. And okay, x2 here has got a first element, 0. So there's no way I can map x2 bijectively with x1 because x1 simply doesn't have a first element. x2 has a least element. But x1 does not. So there can be no such isomorphism. Okay, so that justifies you in claiming that these two are not isomorphic. But now we just need some, by injections, one-to-one maps, x1 into x2 and x2 into x1. So just saying now what we need to do next. We just need one-to-one maps of x1 to x2 and x2 to x1. So let f go from x1 to x2. And all we do is say let f of r be r on 2. We just halve the rational that's there. So it's gone off the page. Here it is again. x1 is q intersect this interval here. So we just halve the rationals. Right? Of course, that sends everything in here into a subset of x2. And it's clearly 1 to 1. And it preserves order. And it's order preserving. And going in the other direction, so here's x2. I need to map it into x1. So the only thing I need to worry about is, this 0 that's here, this first element. Right? Well, I'll just send that to a half. So I'll let g of r now be a half plus r on 2. So now you can see what happens. 0 gets sent to a half, which is within the interval x1, inside. Right? And then all the other things just get sent to a half plus half of the other rational. Right? So in fact, g is going to send x2, where does it send it to? Into a half, and actually it doesn't use the 0.1 at the end. But again, it's 1 to 1 and order preserving. So we're done. So again, g is taking x2 with less than isomorphically to just the range of g with less than. And here this was a half 1 intersect q. Okay, any questions then about that?